Okay, this is the last new material, and then we're gonna start reviewing for the final. Yay! So, this video will go through two more types of hypothesis tests. They're both called chi-square tests. So this symbol right here is the Greek letter chi. And then obviously this is square. So we've got two types of chi-square tests. There's a goodness of fit and there's a test of independence. And that's what we're going to go through on this. We're supposed to go through chapter 29 as well. I'm just going to skip that chapter. I don't see any value in it. Basically, it's just giving you some precautions and stuff. And we've already discussed everything that's in that chapter. So we're just going to end right with chapter 28. Okay, so we're going to start with goodness of fit tests. And that's, a goodness of fit test is just what it says. It's testing if the data fits what it's supposed to fit. So if we go into Canvas, hold on. Don't know if I am out of, let's do this. Oh, good, we're still there. Okay. I couldn't remember if I was in my inbox or what on this. Okay, so on Canvas, we're going to look at the cheat sheet. Remember, you don't get this on the test, but it's a good study source. We are doing chi-square goodness of fit test, this right here. And what we want to know is what we observe, what we would expect to happen. And hopefully my dog doesn't bark throughout this whole video. Hey, Juno, come here. Juno, come here. Come on. Come on. Good girl. Thanks, hon. Okay, so you start a chi-square goodness of fit test with the null and the alternative. And for chi-square, the null is the observed matches the expected. The alternative is the observed does not match the expected. And then we go through these steps to get down to our conclusion. Okay, this is what the chi-square curve looks like. It's different than a normal or a T-curve. You can do chi-square in your calculator, just like you can do shade norm and shade T to get areas under those curves. You can do shade chi-square, but we're going to use this chi-square CDF in our calculator to get that. So if we look at our cheat sheet, this is what you're going to type in your calculator. And this is the steps to get there. So we can look back on our notes. And it says it here as well. You go to second. Ooh, that's an arrow. Vars. And then choose chi-square CDF. And type in the info you know. So we can do that with this information. I now live very close to Hill Air Force Base, so frequently we get airplanes over our heads. And you might be able to hear that right now because it's quite loud. Okay, so we go second vars, distribute, so it just should automatically pop up on that first option. And we're going to do chi-square CDF. Do not choose option 7, PDF, we want CDF. And then this problem in our notes said chi-square with 6 degrees of freedom to the right of 8.7. So this is what we're going to type in. Notice we're no longer using 10 here. 10 is not big enough with this curve. You'll see 10's right here. So we need a number that's big enough. So we're just going to stick with 500. That's way big. Okay, so, and it's always going to be to the right on a curve. So the upper should always be to the right of the number given. So the lower will be the chi-square number. The upper will always be 500. So we've got 8.6, is that what it was? 8.7. 500 with a degrees of freedom of 6. Okay, move the decimal 2 places to the right, and that number is 19.1. We can do it with this to the right of 8.5 with a degree of freedom of 15. So we're going to go chi-square CDF 8.5 to 500 with 15 degrees of freedom. Second vars from the distribution or the main screen, select options 8. 8.5 to 500 with, my memory's failing, 15 degrees of freedom. Okay, and that is 90.2. So what I want to discuss here is 8.7 and 8.5. They're basically the same number, but these percents are significantly different, and it's because of our degrees of freedom. The degrees of freedom makes a huge difference because our chi-square test, the amount of area in this tail here, we're going to let this airplane get past. Maybe. Okay, the degrees of freedom determines how much is in the tail. So sometimes there's a lot more in the tail, and sometimes there's very little in the tail here. So that's why we see a difference in those numbers, because sometimes there's more area if you have a bigger degree of degrees of freedom. Okay, find the area with 2 degrees of freedom to the right of 6.57. You could just again type that into your calculator. Chi-square 6.57 500 with 2 degrees of freedom. Oops. $6.57. Okay, and that is 3.7%. So that's how we do the chi-square area in our calculator. That's like shade norm and shade T. Now we're actually going to do a problem here. So M&M years ago said, and you can find this on the website, that in a pack of just regular milk chocolate M&Ms, the distribution of colors should be about this. 13% brown, 14% yellow, and so on. So if we were in class, we would each get a pack of M&Ms and we'd count our distributions up. We're not, though. So we're going to take the results from a previous trimester, and see, when I've done this before, my pack had 7 browns, 36 yellows, 19 reds, 26 blues, 7 oranges, and 10 green. So if you add all those up, that gives you a total of 105 M&Ms in that pack. Well, we can calculate the expected. So the observed is what actually happened. The expected is the number you would expect for each color in that pack of M&Ms. So out of 105, we would expect 13% of them to be brown. So out of 105, 13% is 13.65. And I'm not going to round. No reason to round. So then 14% of 105, 14.7. We already did 13%. So I'm just going through and multiplying this as a decimal by this number. So the last one, 0.16 times 105 is 16.8. Okay, this is the number of M&Ms of that specific color you would expect. It's okay that there's decimals. This is just an expected, so it doesn't have to be realistic. You'll notice if you add that up, it does add to 105, because we should get 105 total, because that's how many were in the bag. And what's making me concerned here is how different this one is, the observed from what we would have expected, and how different this one is from the observed to what we would have expected. So what we want to know is M&M's is the M&M website incorrect? Is their data wrong? So we're going to go through a chi-square goodness of fit test and see if these numbers are so different that we're concerned that they're lying to us, or if it's okay. And if, yeah, it's different, but that's just due to chance error. So the null, with our hypothesis test, the null is the observed counts are consistent with the expected counts. So what we got is what we expected to get. The number of M&Ms of each color is about accurate compared to what we should have gotten. The alternative is the observed is not consistent with what we expected. We require expected values of at least 5 in each category for the test to be valid. So you don't need to worry too much about that, but what it's saying is you need 5 or bigger in each of these cells. Okay, you can figure out a chi-square number to get your test statistic. So remember how we used Z equals observed minus expected over SE, and T was essentially the same thing. We're not using Z in this, we're using chi-square, and this is the formula for chi-square. And you can do that by hand, but I don't see any reason to do it by hand because you can also do it in your calculator. So that's what we're going to do, is have our calculator calculate this for us. Real quick, what it's doing is it's doing observed minus expected squared divided by the expected. So we would do 7 minus 13.65 squared divided by the expected. Figure out what that is. Do it for this one, this one, this one, this one, this one. So do it for all of them and then add those together. And that is your chi-square statistic. So that is this number that we've been given in those previous problems. So you can go through and do that by hand with the formula if you want to. But again, I don't see any reason to because our calculator can do it for us. So we're going to do it in the calculator. Oh yeah, this wants us to do it by hand. So this would have us go through and write those numbers down for each of them and total it up to get chi-square. You can do it by hand by following these steps. So type the observed into L1, type the expected into L2, and then we're actually going to just do the full test, and we'll get our p-value as well as chi-square at the same time. Okay, so we're going to clear out the previous list. So go stat, edit. There's nothing in that previous list, so we're going to type in list 1. Our observed, we observed 7 brown, 36 yellow, and so on. Okay, we expected 13.65, and it is important that you do observed in L1, expected in L2. Okay, so we've typed those into L1 and L2. And then to calculate chi-square, we follow these steps. We go to stat, arrow over to tests, and then choose option D. So stat, arrow all the way over to tests, and then you can arrow down or up. It doesn't matter. You just need to get all the way down to this option D, chi-square goodness of fit test, except I need to get out of this. Okay, so stat, tests, option D. We're going to use L1 and L2. The degrees of freedom, just make sure it's right. It should be calculated for you, but the degrees of freedom, remember, is just the number of, well, in previous chapters, it's been the number of samples minus 1. So in this one, it's the number of categories. So we have brown, yellow, red, blue, orange, and green. Those are our categories. That's 6 total categories. So the degrees of freedom is 5. Okay, and it tells us that chi-square is 48.3, and our p-value is this really teeny tiny number, that second line down. It's E09, negative 09. That means you move, it's scientific notation, you move the decimal to the left 9 times, so it's essentially 0. So what we're going to say here is chi-square equals that 48.3. Let me make sure I remembered that number right. Yes. So you can go through and do the formula, this observed minus expected squared divided by expected, to get each of these and then add them up, or you can just tell your calculator to do it. Okay, we already talked about this. There were 6 categories, so we did 6 minus 1 was 5. And then we can do chi-square CDF. Um, 48.3 to 500 with 5 degrees of freedom. You can type that in, but there's actually no reason to type it in because we already got that answer. There's 2 different ways to do this test, and this chi-square goodness of fit test that we got from stats option gives us the p-value. It's this, again, second number, 0%. The 3.5 blah, blah, blah is 0% because you move the decimal twice. So we reject the null because it's less than 0 or less than 5%. So bag is not distributed as we would have expected it to be. That's the colors in the bag are not distributed as expected. Okay, this one, is the die fair? So on a die, remember there's outcomes 1, 2, 3, 4, 5, 6. If it's fair, you should get equal amount of each of those numbers. So this is what we observed. When we tossed the die 240 times, we observed each of these outcomes. We got 38 ones, 26 twos, and so on. What we would have expected is 1/6 of the 240 to be each of those numbers. So if we take 240 and divide it by 6, that's 40, meaning we would have expected 40 of each of these. So what we want to know is the die fair? So our null, die is fair. Our alternative is the die is not fair, die is loaded. Nope, just wrote those down. Okay, test statistic. Let's just do the chi-square GOF test, goodness of fit test, to just have our calculator do all of the work for us so we don't have to do it by hand. So we're again going to follow open the wrong one. These steps. Remember, that's on the third page of this cheat sheet that you're going to want to memorize. As you're working with these problems, you'll memorize it. So we're going to go into L1, stat, edit, clear out what's already in there, and find. Okay, so we had 38. Whoops, it turned sideways. $26, 3, 4. Whoa, okay, sorry. We got 32 threes. We got 44s, 65s, and 44 sixes. But we should have gotten, if the die was fair, we should have gotten close to 40 for each of these. Or we'd expect to get 40 for each of these. So we want to know if these numbers are different enough from 40 that we think the die is loaded. It's not fair. So we've got those numbers typed in. We can do chi-square goodness of fit test by going to stat, arrow over to tests, and choose option D, goodness of fit. If you're on just a regular calculator, it might be easiest to just scroll up. And notice it tells us our degrees of freedom is 5 because we've got 6 categories. We've got 6 different sizes of the die. 6 minus 1 is 5. Okay, so our chi-square, that top number is 17. Our p-value, move the decimal twice, it's 0.45%. And also, you'll notice this last column, or last row, it tells you the component. So it's telling you if you went through and did that observed minus expected all squared divided by the expected, it would give you each of these numbers, so 0.1 for one, 4.9 for the second one, and so on. So 17 and 0.45%. 5 degrees of freedom, chi-square is 17, p-value is 0.45%, which is less than 5%. So we failed to accept the null. There is evidence that the die is loaded. These are my favorite tests because they're so quick. The calculator does most of the work for us. Okay, here's another one. Yeah, we'll do this one. So we got this bus, and this ridership shows you how many people ride the bus each day of the week. So the Regional Transit Authority is concerned about the number of riders on one of its bus routes. And setting up the route, the assumption is that the number of riders is the same every day, Monday through Friday, so every weekday. So let's add up the total number of riders and average that so we can get what we would expect it to be. Because this is what we observe it to be. So we expect, if we do 71 plus 59 plus 51 plus 66 plus 53, that's a total of 300. 300 divided by 6. No, sorry, 5, because there's 5 days of the week. is 60. So if there's the same number of writers each day, it should be 60. So we're going to see if these numbers are different enough from 60 that the bus route may want to consider changing on a specific day of the week or stuff like that. So you can go through and you can find the component for each of these by doing observed minus expected, all squared, over the expected, over the expected, I did that backwards. Find each of those, add them all up, or we can say calculator, do the work for us. So that's what we're going to do. So stat, edit, and we can change our lists to the accurate list for this. Sorry, that was a weird noise. I hit graph instead of the correct button. So 71, 59, 51, 66, 53, and then 60. Okay, there's 5 days of the week, so we've got all 5 of them there, which means the degrees of freedom is going to be 4. Keep that in mind. Go to stat, arrow all the way over to tests, and then arrow up or down until you get to option D. It did not automatically fix our degrees of freedom, so we're going to have to do that. It's 4. Because 5 minus 1 is 4, and then we calculate. So chi-square is 4.8. P-value is 30.8%, and it does give you each of the individuals. So for Monday, our chi-square component was 2.02. On Tuesday, it was 0.02. On Wednesday, it was 1.35. Thursday, it was 0.6. Friday, it was 0.8182. The important numbers here are 4.8 and 30.8%. So, we'll come back to the hypothesis test. I forgot to write that. 4.8 is pretty small, chi-square. So when we get a p-value, let's see, degrees of freedom was 4, p-value of 30.8%. I'm not surprised. What that means is we accept the null that's bigger than 5%. But we better go back and write the null. And I'm going to say ridership is about the same each day. Meaning there's the same number of people on the bus each day. We're talking specifically Monday through Friday, so I'm going to say each weekday. And the alternative is ridership is not the same each weekday. So we accept the null. It appears that ridership is the same each weekday. Okay, is this going to give us any more info if we do this one? Or is it just, yeah, it's just another one of these same problems. We're not going to do this one. Okay, last is test of independence. So let's look at our cheat sheet. Chi-square test of independence, you are testing for independence, and I'll explain what that means in just a minute. You'll see these steps. We're going to be doing a lot of steps in our calculator on this one, just like we did the chi-square goodness of fit in our calculator. So really when you're studying for the final, what you'll want to do for chi-square goodness of fit and chi-square test of independence is memorize these steps. Typically on the formula sheet, you will have calculator instructions as well. I'll have to check the formula sheet I've been provided with, and I'll let you know. I'll have a video with info about the final in the final module, so you can look there to know what you need to memorize and what you'll be given. Okay, the word independence means one thing doesn't influence the other. So chi-square test can be used to decide if two qualitative variables, qualitative means non-numbers, are independent. That is, if they are related to or influence each other. We set the null hypothesis to be that the variables are independent, so the two variables have nothing to do with each other. And we look for evidence to reject that null. We look to see if maybe, actually they are dependent. So our null is going to be variables are independent. And the word independent can also be not associated and not related. The alternative is the opposite of that. Variables are dependent. Associated. Related. Okay, this formula will look familiar. It's the same chi-square formula, but we're now going to be working with matrices. So we've got a couple new formulas here, and I'll show you how those formulas are used on the next couple slides. Okay, so each person in a random sample of 661 teachers was classified according to a job satisfaction variable and also by teaching level, resulting in the table below to conduct a hypothesis test to determine if job satisfaction and teaching level are independent. So we have two variables here, teaching level and job satisfaction. And we are given this matrix. Okay, some of you, the word matrix is totally new to you. Matrix is just a fancy way of saying a table. And then there's some totals here as well, but it's the inside numbers that we care about. So this 224, we're just looking at a two-way frequency table. It's saying 224 of the 661 teachers teach high school and are satisfied with their job, versus 171 teach high school and are not satisfied with their job. So there's all that information, or how we read that table. Again, this is the stuff we care about here. Whoop! Okay, the hypothesis is the two are independent of each other. So our null is job satisfaction and teaching level, whether you teach high school or elementary, is independent of each other. Elementary teachers aren't happier with their jobs than high school or vice versa. So, the alternative is the opposite of that. Job satisfaction and teaching level are dependent. High school teachers are happier than elementary teachers, or vice versa, with their jobs. Okay, the test statistic is chi-square. So with chi-square, we have our observed. And the observed is the four numbers that we boxed in this previous slide. 224, 171, 126, 140. Okay, in order to calculate chi-square, we need the sum of the observed minus the expected squared divided by the expected. That's our formula from here. And we've been having our calculator do that, and we will have the calculator do that again on this one in just a minute. But I want to show you what the calculator is going to do. It's going to create another table for expected. So it's going to give you four numbers in this form. And this number will show what it should be or what you would expect it to be for high school teachers that are satisfied. So cell by cell, they're the same. It's just the observed versus the expected for those. And then your calculator will take the observed minus the expected, square it, divide by the expected, and sum up these four to come up with what chi-square equals. So let's look at our steps here. We're going to put the observed data into matrix A. So remember, matrix, that's just a word that basically means table. So we're going to go, instead of into our lists, we're going to go into matrices or a matrix. If you notice on the right-hand side, the button that says math, third from the top, if you go second math, second, the button right underneath that, X1, you get into a matrix. So one more time, I did second and then matrix. And we want to edit a matrix. So we're going to arrow over to edit and edit matrix A. And, oh man. Okay, the first thing you have to do is tell it the number of rows and columns. This is a 2-row, 2-column matrix. And then it just automatically populates that or creates that matrix, and you have to type the numbers in. So let's see, the numbers we were given were 224, 171, 126, and 140. And we don't care about the totals. Okay, so this is kind of like typing into our list, except it's not a list anymore, it's a table because each individual number has two variables associated with it. Okay, second step, whoops, wrong one. So we typed it in by going second, x to the -1, edit, enter, type in our matrix. Then we're gonna go chi-square. And stat, test, and option C. So the same way we got to chi-square goodness of fit test, but this time we're going to go stat, arrow over to tests, and choose option C, just a chi-square test. Our observed matrix, we typed it into matrix A. It's going to automatically populate the expected into matrix B. So we're going to hit calculate. And it gives us some numbers here, so let's write those down, and then we'll talk about how to use each of these, except there's... Okay, so 5.6 for chi-square, P is 1.8%. So degrees of freedom was 1. I'll show you how to get that in a moment. Chi-square was 5.6. P was 1.8%. Okay, what happened here was our calculator automatically created this and then automatically did this to get our chi-square number. So let's find where those expected numbers went, because typically on finals, I see a question that asks you to fill in the number for cell B. And so if we want, or like cell D, C, D, A, if we want those numbers, we have to find them by going back into matrix B, which is these steps right here. So we're going to go second, X1, arrow over to names, and just choose matrix B and hit enter. And it shows us those numbers, 209.2. And so on. So if I had a question on the final that gave me a blank expected value table and said, what is the value or the chi-square component? That's what each of these are called, chi-square components. For cell A, I can just look on my calculator and, oh, where'd it go? Tells us it's 209.2. Cell B is 185.8, cell C is 140.8, and cell D is 125.2. Okay, degrees of freedom is equal to the number of rows minus 1 times the number of columns minus 1. So we have 2 rows. Remember, rows are this way. Columns are like a column on a porch or in a castle. It's up and down. Okay, this number is smaller than 5%, so we reject the null or fail to accept the null. Our null was that they are independent, so we're going to say there is evidence that job satisfaction and teaching level are dependent. And we can go back and look. There's a higher percent of high school teachers that are satisfied compared to unsatisfied versus smaller percent satisfied to unsatisfied for elementary. So if you're going to become a teacher, high school is where it's at. Okay, gender and handedness. Handedness means are you left-handed or right-handed or ambidextrous? We want to know if these two are independent or dependent. So does it look like more women are left-handed than right-handed, or more women are ambidextrous than men? And I'm just choosing that because there's bigger numbers here. But we also see there's more women questioned. So we have this quick, easy chi-square test of independence. So we don't have to take that into account. We let the calculator take that into account. So our null, gender and handedness are independent. It's always independent. Our alternative is the opposite of that. Oh, Juno. Okay, test statistic. We're just going to use our calculator for that. So I'm going to move over to the next slide. And actually, we're going to move back a slide so we can type these in to our calculator. Okay, we're going to go second, x to the negative 1, so we can get into our matrix. Arrow over to edit. We're going to edit matrix A. So this time it has 2 rows and 3 columns. Oh, I lied, sorry. 3 rows and 2 columns. And if you're not sure, just take a guess. It automatically creates the matrix, so if it's the wrong dimensions, just switch the 2 numbers. But this is a 3x2, rows before columns. And then we can type those numbers in. Whoops. Okay, then we just need to tell our calculator to do all the work for us. So we go into Stat, arrow over to Tests, choose option C, chi-square test. Our observed is typed into matrix A. We want the expected to go into matrix B, so we hit calculate. And chi-square is 0.16. P is 92.1%. P always gets multiplied by 100%. The chi-square never does. Oh, and then degrees of freedom, we had 3 rows, 2 columns, 2 times 1. Degrees of freedom is 2. So p-value again was, and it tells you degrees of freedom, their 3rd row from the top, 0.16 and 92%. Okay, technically chi-square is the test statistic, so I should be writing it over on this one. It just doesn't matter too much. It's all just work to get down to our conclusion. So 92% is very, very high. So it's greater than 5%. So it looks like evidence that they are dependent. We accept the null or fail to reject the null. I should never accept the null. Whoops. Fail to reject null. Sorry, my dog has been very clingy lately, which is cute, but it means she has to be right by my side when I'm recording these lessons. But then she likes to bark at every little noise too. Independent. I am certain I spelled that wrong. I'm sorry. Maybe I didn't. Okay, let's do this one. Birth weight and high school graduation. I'm skipping the Titanic one. Does birth weight affect high school graduation rates? Data based on a Time magazine article are listed in the table below. Conduct a hypothesis test to determine if birth weight is independent of whether the subject graduated from high school by age 19. That is our null. Birth weight and graduation age are independent. So the alternative is the opposite. Birth rate and graduation rate are dependent. If you're born premature, you're not going to graduate on time, is essentially what that says. Okay, test statistic is chi-square because this is a test of independence. We're just going to use our calculator to do all the work for us. So this will be matrix A. Okay, so we're going to go second, matrix A, we're going to edit. Let's see, we need a 2 by 3, or sorry, a 2 by 2. And the numbers are 8, 42, 86, 64. And then we just go stat. Whoa, hold on. I got into something weird. Stat, arrow over to tests, choose option C. And calculate. Okay, chi-square is 25%, P is 3.9486, blah, 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 E negative 0.7. So this is another scientific notation one where we need to move the decimal 7 places to the left, making it 0%. So chi-square is 25. What was it, 25.7 or something like that? Yeah, 25.7. Degrees of freedom was given to us. It was 1. And p-value was essentially 0%. So we fail to accept the null. And it looks like they actually are dependent. So there's evidence to believe that birth rate and graduation rate, or age, are dependent. Notice it's not causation, it's just a dependence or a correlation there. It's probably something to do with parenting. Parents who don't take good care of their baby while pregnant tend to have babies prematurely. And they also don't parent as well while they're in school. So we've got some biases or some confounding factors that go in behind the scenes there. But what we were trying to say before I got distracted is birth weight and graduation rate are, that is an and sign, are dependent. Okay, and that's it. Again, we got rid of chapter 28, so you just have this assignment for chapter 20, or sorry, we got rid of chapter 29, so you just have this assignment for 28. As soon as you get done with this one, start looking into the info on finals, or on our final. Quiz 5 is going to help you get logged into the USU Canvas page, because that's where we will be taking our final. We're going to be using a program called Panopto. No, not Panopto, sorry. Proctorio, something like that, Proctorio, where it observes what you do while taking the test. So if you are cheating, I will be notified and I'll have to get rid of your test, your test score. So again, quiz 5 will help you get logged into Canvas.